Good day to everyone. Welcome back to our classes. Today, the sixth lesson of chapter 4, Moving Charges and Magnetism, grade 12. Okay, today we will learn a very important law from this chapter. You already learned Biot-Savart law. So today we are learning an alternative form of Biot-Savart law. Okay. This law is called Ambience Circuital Law. The name of the law is Ambience Circuital Law. Okay, this law is applicable to open surfaces and some currents are passing through the open surface. What is an open surface? See, you can see this is a cylinder. This surface, the front surface, that circular surface, that is an open surface. This circular surface is an open surface. Okay. When you consider your laptop screen, it is an open surface. And this open surface has a boundary. Okay. In the case of this object, the boundary is circular. Okay. So you consider an open surface and some currents are coming through the open surface or moving into the surface. Okay. And in such cases, we can find out the strength of the magnetic field along that boundary. So all open surface, there is a boundary. That boundary will be a closed loop. Okay. When you consider a cylinder, when you take the cross section, that cross section is an open surface. The boundary will be circular. When you look at your screen, laptop screen, the boundary is rectangular. Okay. So Ampere's law dealing with the open surfaces and some currents may be coming in or out of the surface. We can apply Ampere's law in such situations. Now I will give the statement of Ambience Circuital Law. Ambience Circuital Law. Okay, so you consider an open surface. This open surface, see, this is an open surface. This is the boundary, circular, the boundary of that open surface, I take as a circle. Suppose some currents are moving into the surface. Okay, I draw in the vertical direction. 1 minute. So this is the boundary of the open surface. Okay, some currents are moving into like this. Suppose one current is moving like this. So many currents, suppose, moving like this. Okay, so you know, due to this current is moving charges. There is a magnetic field, and magnetic field, if you imagine a straight conductor, okay, magnetic field will be around the concentric circles. This concentric circle we consider Amperian loop. I told you this circle is the boundary of the open circular open surface. Okay, when current is passing through it, I am finding the magnetic field around this current. So you consider this closed loop. This is known as Amperian loop. And this loop, we can divide it into a very large number of infinitesimally small length. See, this is one such length DL. So we can divide it into large number of infinitesimally small number DL. And when we consider this DL, magnetic field is along the tangent. You know the direction of magnetic field, that will be along the tangent to this circular loop. That is given by, you consider a straight conductor moving, current moving up, so magnetic field lines will be circular loop given by right hand thumb rule. So here magnetic field is into the plane of the paper, and that is parallel to the DL. Okay, you consider any point on the loop. When you consider this point, magnetic field and the DL will be always parallel. When you consider a DL here, DL on the left side, magnetic field will be here out of the plane of the paper, and DL length will be parallel. So magnetic field is always tangential to the path, that length, the DL. Remember this. So we are finding B dot DL. B dot DL for this particular element, say AB. Okay. And there are so many such elements for this loop. This loop is divided into infinite number of such small elementary lengths DL. When you add all this, we call it is integral B dot DL. Okay. So first we find out BDL, B dot DL for one small element. Okay. Now you add the B dot DL for all such elements, and these elements are infinitesimally small. So that addition is known as integral B dot DL. This is known as line integral of magnetic field. And this is equal to mu0 times the current. The current is the net current, total current passing through this loop. This is the statement of Ambience Circuital Law. I will give the statement. The line integral of magnetic field around a closed loop is equal to mu0 times the total current or net current passing through the closed surface, closed loop. So what is the statement of Ampere's law? Ampere's law states that the line integral of magnetic field around a closed loop is equal to mu0 times the total current passing through the loop. Okay, this is Ampere's law. Ampere's law. The line integral of magnetic field around a closed loop is equal to mu0 times the total current enclosed by the loop. This is Ambience Circuital Law. Okay. Now we have to discuss the applications of Ampere's law. We mainly do three applications. Using Ampere's law, we can find the magnetic field near a straight conductor carrying current. Second is we can determine the magnetic field inside a solenoid. And third application is we can find the magnetic field due to a toroid. So we will discuss one by one. First application. So main heading is applications of Ambience Circuital Law. Applications of Ambience Circuital Law. First one, to find the magnetic field near a straight conductor. Carrying current. You can find the magnetic field near a straight carrying conductor. Magnetic field near a straight conductor carrying current. You imagine a straight conductor or a straight wire. So I am drawing in little bigger size. This is a straight conductor. Okay. This cross section is circular in shape. Okay. You know, the cross sectional area is circular. That cross sectional area is an open surface. Okay. And current is passing through the conductor. Current I is passing through the conductor. Okay. So current will be passing in this way, like this. And I'm going to find out the magnetic field at a point outside the conductor. So to apply Ampere's law, you need an open surface. That open surface is a circular area, and we have to consider a loop. That loop is known as Amperian loop. And you know, on this loop, magnetic field is always tangential to the length. So let me find the magnetic field at this point, P. Okay. So magnetic field at a point outside the conductor. So you need an Amperian loop. In Gauss's theorem, you consider a Gaussian surface. Here you consider an Amperian loop. See, I'm drawing a circular loop, this one, passing through the point P. And you know, at this point, magnetic field, you can use the right hand thumb rule to find the magnetic field direction. Current represented by thumb, direction of field lines is in this way. Okay. So it will be, magnetic field will be along this. Imagine a small elementary length here. This length is dl. So dl and magnetic field are parallel. At every point on the loop, they are parallel. Now, radius of this conductor is, say, R, capital R. And radius of this Amperian loop is small r. Small r is the radius of the Amperian loop. Amperian loop. Okay, now we can apply Ambience Circuital Law. What is the statement? Closed integral B dot to dl. This is known as line integral. Equals mu0 times the current through that surface, through the enclosed by the loop is I only. Okay. Closed integral B dot dl is B dl cos 0, cos theta. Theta is 0 here. B and DL are parallel. Mu 0 I. B will be constant on that loop. On that particular loop, B value is constant. B into integral DL equal mu 0 I. From this, B into, what is this integral DL? When you add this all DL, integration means adding all the DL lengths, you will get circumference of the loop, 2 pi R equals mu 0 I. From this, what is B? Mu 0 I by 2 pi R. So this is the equation for the magnetic field at a point outside a straight conductor carrying current. V equals mu 0 I by 2 pi R. Here mu 0 I pi constant. So we can write V is inversely proportional to R. So we found the equation for magnetic field at a point outside the conductor. So we have to imagine an Amperian loop outside. And remember, on the Amperian loop, B and DL are parallel. Okay. So at a point outside, V is inversely proportional to R. V is the strength of the magnetic field. Now I am going to find magnetic field at a point inside the conductor. For that, you consider a point inside the conductor. Okay, at a point inside the conductor. See, you consider a point here, this point P dash. So we need to take an Amperian loop. So draw an Amperian loop. Black line and drawing this Amperian loop. Its radius is small r. When you consider the point inside, small r will be less than capital R. What is capital R? Radius of this circular, radius of the conductor. Okay. Now magnetic field at a point inside the conductor. So first we found magnetic field at a point outside the conductor. Now magnetic field at a point inside the conductor. For that, you imagine Amperian loop inside. Okay. Consider an Amperian loop of radius small r. This small r is less than capital R. What is capital R? Radius of the conductor inside the conductor. You can apply Ambience Circuital Law. What is Ambience Circuital Law? Closed integral B dot dl is equal to mu 0 times I. But here we imagine that the current is flowing through the entire cross section of the conductor. We imagine that current is uniformly distributed over the entire cross section of the conductor. But you can see current is for this smaller loop, that area will be less. So total current will be less now in this loop. Current through the smaller loop will be less. We have to find out current passing through that smaller loop. So I put this current as I dash. What is this I dash? Current passing through that smaller Amperian loop. That we have to find out now. For finding that, we imagine that current is uniformly distributed over the entire area of cross section of the conductor. That means current through the complete cross section of the conductor, current through the area pi capital R square is I. So this I is distributed through the complete circular area. So current through the area pi R square is I. So what is a current through unit area? Current per unit area of cross section. It will be I by pi R square, right? Current capital I is for the full cross sectional area, flowing through the full cross sectional area. Current flowing through unit area of cross section is I by pi R square. Now we can find out the current through the smaller area. Therefore, current passing through the smaller area pi R square is I dash equals, how will you find out? Current per unit area into the smaller area. So this is the current passing through that smaller ambient loop. Okay. Why we are considering smaller ambient loop? You need to find out magnetic field inside the conductor. Now you put it in the equation, Ampere's law. What is Ampere's law? Closed integral V dot dl equals mu 0 times I dash. What is this I dash? Pi R square by pi R square into I. I is the total current enclosed by the ambient loop. This is V dl. You know, V and dl are tangential. Mu 0 pi R square by pi small r square by pi capital R square into I. Now B is constant. B into integral dl will be equal to mu 0 pi cancel R square by R square into I. And you know already integral dl is 2 pi r. But integral dl equals 2 pi r circumference. Therefore, B into 2 pi r equals mu 0 r square by capital R square into I. That one smaller you can cancel. And you will get V as mu 0 I divided by mu 0 I into R divided by 2 pi R square. So this is the equation for the magnetic field inside the conductor. So what is the equation? B is equal to mu 0 I by 2 pi R square into small r. Here mu 0 I 2 pi capital R are constant. So B proportional to R. So remember, outside the conductor, magnetic field is inversely proportional to R for outside points. Inside the conductor, inside points, B is directly proportional to R, small r. What is the small r? Distance from the center to the point, center of the loop to the point. Okay. Now we can plot graphically this variation. So when you move from the center of the loop till the surface, magnetic field is proportional to R. Magnetic field will increase. And outside point B is inversely proportional to R. Magnetic field decrease. So from center to the surface, magnetic field will increase. From the surface onwards, as you move away, surface of the conductor onwards, as you move away, magnetic field decrease. Now, what will be the magnetic field at the surface of the conductor? At the surface of the conductor, magnetic field, surface of the conductor, small r will be equal to capital R. Okay, the radius of the ambient loop will be same as the radius of the conductor. So what will be B? I to take it as B0 is equal to mu 0 I by 2 pi R square into R. So what you are getting, this R cancel, you will get mu 0 I by 2 pi R. This is at the surface. So the magnetic field is maximum at the surface. Okay. So magnetic field increases from the center of the conductor till the surface, and then it decreases. We can plot it graphically. So I am drawing the graph variation of magnetic field with the distance from the center of the loop of the conductor. Okay, this topic is very important as a derivation, and also they can separately ask to draw the variation of magnetic field with the distance from the center. So along y-axis, I take B, and along x-axis, I take R. Okay. Now, you know, from center, 0 distance to this radius, magnetic field B directly proportional to R. So this will be a straight line till the surface. This surface, you take capital R. Radius become capital R. Okay. So till the surface, you know, B proportional to R. As you move away from the surface, B inversely proportional to R. So graph will be like this. It will be like this curve, like this. So here B is inversely proportional to R. Okay, dear children, this derivation and the graph is very important. Okay, so we learned today Ambient Circuital Law and one of its application. What is Ambient Circuital Law? Actually, it is an alternative form of Biot-Savart law. Okay, what is the statement? The line integral of magnetic field around a closed loop is equal to mu 0 times the total current enclosed by the loop. Okay, so this is the loop. You can see many currents passing through it, right? I1, I2, many currents, I3, etc. So closed integral B dot dl equals mu 0 times I. I is the total current. Remember this. So, dear children, today I end the class. Thank you for watching. Like the video, share the video, give your comments. We will meet you in the next class. Thank you for everyone. Goodbye.